Okay, YouTube, this is my follow-up video to my last video in which we introduced solving rational equations. What I would like to do in this video is take a little bit different approach to it, and we say, let's consider these two equations. So we have some y as a function of x here, and another y2 as a function of x. I want to find all values x for which y1 is equal to y2 and check. So the first thing I basically want to notice is we could say, well, if y1 is equal to y2, then these two expressions would be equal here. And so we could just basically list them. We say 1 over x plus 4. That's being added to 1 over x minus 4. And then we'd say that I want to set this equal to 22 over x squared minus 16. So if we're going to solve this, recall the first thing we want to do is list any values for which our denominators would be equal to 0, which means we need to factor both sides of this expression's denominator. So we have 1 over x plus 4. That's already factored. It's just its only factor is x plus 4. Here we have the only factor is x minus 4. And then the right side, I notice that this is a difference of squares, so we say it's x plus 4, x minus 4. If we were to factor that, okay? And so we say, setting all of those equal to 0, we'd say, well, if I set x plus 4 equal to 0, or I set x minus 4 equal to 0, any of the factors set equal to 0 here, I get x is negative 4, and I say x is positive 4 here. Sorry, that's what you get, x equals positive 4. So those right there in terms of solutions, okay, we'll put the solution set over here. The very first thing we want to do is we want to say, well, whatever the solutions are, they can't be either a positive or a negative 4. It couldn't be either of those in our solution set. But the second thing is, to solve this, what we're going to do is we're going to find the LCD. So the LCD is one of my favorite things to do, is say, well, you list all the factors of the very first fractions denominator you have over here. And I notice that this only factor is the x plus 4. Since I have all these other denominators factored, what I want to do is add to this list any factors that aren't already on the list. So when I look at this second denominator, I'd say, well, this already has an x plus 4, but it doesn't have an x minus 4. So we'll add that to the list. We say x minus 4. And so now that's on the list. Boom, check, boom. Okay, I've got this on the list. And then I say, well, you know, are any of these not already on the list? Well, I've already got these on the list. Okay, so our least common denominator would be the product of these two things. So I'm going to cheat a little bit here. I'm going to squeeze these in. I'm going to say, well, I'm going to take both sides of this equation times x plus 4 and x minus 4. Remember, we just go ahead and leave that LCD that we're multiplying by. We're going to leave it factored because, well, it's just messy if you don't. So if I distribute this through, maybe we start with the right side here. I notice that when I distribute this through, basically these factors just cancel out top and bottom, and I get left with 22. And on the left side here, if I take x plus 4, x minus 4 times this over x plus 4, the x plus 4's cancel out, and I'm left with x minus 4 times 1. So I get x minus 4 times, I'll even write times 1, okay? Plus, now if I distribute it over here, the x minus 4 is cancel out, and I get left with x plus 4 times 1. So I get x plus 4 times 1. This equation is really actually a really easy one to solve. We say, well, 2x's on the left. The positive and negative 4 cancel out. 2x's equal to 22. So if I divide both sides by 2 now, I get x is equal to 11. So our solution set here is the set containing the element 11. I don't have to exclude this because the only ones we had to exclude were positive and negative 4. So the last thing I want to do is I actually went and I took these two equations and I typed this one in for y1 on my calculator. Notice I used a lot of parentheses, 1 over the quantity x plus 4 plus 1 over the quantity x minus 4. And then I typed this in for y2, which is 22 over the quantity x squared minus 16. And if I go hit graph now, you're going to notice some really funky looking graphs. Actually, I got to go turn these on here. But rational equations, they don't show up very well on graphing calculators. They do better in Desmos. But you'll notice at negative 4 and at positive 4 here, our graph looks really crazy because these are points at which it looks like your graph got graphed, but actually it doesn't exist. We say it has vertical asymptotes there. And what we're looking for, what are any x values for which our y values would be equal? And we know it happens out at 11. So one way we could do this is we could say, well, let's change our window to go from like maybe on the x-axis 0 and we'll go out to 20. And I want my scale to be by 5s. Okay, I want to go by 5s. And as far as my y-axis here, you know, I don't know what they're going to come out to be. We'll just go ahead and hit graph. So we say here's the right side of the graph. 11 is going to be right here, just beyond the middle here. And we say that these two graphs are equal about here. So I could even zoom in around that spot. I could say, well, zooming right now, it says x is 10, y is 0. That's about a good spot. We know that at x is 11. Here's x is 5 right here. At about 11, these two graphs are going to collide right there. And so we can certainly use the intersect function behind our trace key. We'd say second trace. We'll hit 5 for intersect. And it'll say first curve, second curve. I'm just going to hit enter and enter since we only have two curves out and it says guess. So it says that these two curves have about this y value when x is equal to 11, okay? And so I would say that they do actually intersect there. And then the other way to look at this is we could look at our table. I'll go to table set here, and we'll start our table maybe at 10. Because I know x is 11. We'll go to table now. That they should be equal. And we can see that for this x value, we have two y values that are actually equal. Cheers.